Hi, my name is Gabel. I work for Wix in Israel. We have offices in the Gabel in Ukraine, and we're setting up a new one in Kiev. So if you want to apply for it or something, feel free to come to me after the talk. I want to apologize in advance. I usually get this talk drunk, but there's no beer at the conference. So I'm going to have to go sober. None of it will make sense if I'm not drunk, so sorry. It is what it is. So let me just get away from the thing so you can actually see. And I just want to set the stage a little bit. How many of you know what DSLs are? Yeah, pretty much everyone. Not much of a surprise. How many of you have implemented or written DSLs in the past? Well, 5 people. That's 5 more than I expected. Cool. Okay, so just a quick overview of what DSLs are, and then we can get to the meat of things. So, a DSL stands for a domain-specific language. So, as the name implies, it is a language designed to deal with a specific application domain. Now, why is that a good thing? Is because once you have a very specific application domain, you can design the language to match that domain. You can make more assumptions, right? You can assume that if you're writing a DSL that deals with, building JSON objects, that is what your users want to do. So you don't have to worry about anything else. So this gives you a lot of kind of freedom to design a language that is more expressive, more concise, a lot more correct by design, or more readable. There are various advantages you can get if you reduce your attack surface, right? So Scala is a general purpose language. You can do pretty much anything, but it doesn't mean that the code that you write is readable. If you saw Baltosh's presentation about macros earlier, he showed how to build JSON serializers with PlayJSON. It looks like hell, right? Because it's pure Scala. You don't want to do that. You want to work with the language that fits your domain as precisely as possible, because there are advantages to that. So, DSLs generally can be classified into one of 2 categories. You have external DSLs that are not part of the host language, right? These are actually designer languages built with specific tools. You need your lexical analyzer and your parser. You need an AST for them, right? It's this whole shebang of external tooling around the language. And there's an explicit lifecycle. If you work with an external DSL, then you need to actually create a parser, read in, get back some sort of data structure that you work with, and then eventually dispose of it. Right, so the lifecycle is very, very explicit. You, as developers, work with a tool to parse some sort of external language, read it in. Examples of that include things like SQL, right? So if you use MySQL or anything of the sort, you build your SQL statements, you feed them into the database engine. The database engine reads them in and executes whatever execution plan it actually parsed out of your SQL. So that's an example. Other examples include Markdown, which probably everyone in this room is familiar with. That's also kind of a domain-specific language. And, oh, sorry about that. Actually, I had a third example, but it was a stupid one, so I removed it. So, anyway. The other category is internal DSLs, and that's what we're going to be focusing on today. An internal DSL is a domain-specific language that is designed within a host language. Right, so in the context of Scala, and I will show examples of that, if you write your tests with Specs2 or Scala test, you get sort of an extended language, right? You get syntax that is designed for testing, for making assertions, but it is Scala. It is built on top of Scala. So an internal DSL is built within a host language, Scala in our case. It does not have explicit tooling. Everything is, everything that you write in an internal DSL must be valid Scala code by definition. You cannot add syntax that is not Scala, right? Anything that your DSL provides must be fully understandable by the compiler. And the lifecycle is implicit, because if you write code in a Scala DSL, it gets compiled along with your program. You don't have code that says, okay, here's where I read in code in this domain-specific language, right? It just gets compiled along with your code. So you do not have control over the lifecycle. On the bright side, you do not need tools. Everything is a lot more simpler. It's a very different flavor of language to design. So examples of that include, as I mentioned before, Scala test, or specs2, same thing really, is a good example of a DSL. This should keyword, it's not a keyword, right? It's a method call, and it does not exist in Scala. The string class in Scala does not have a should method. So that's an extension that the domain-specific language designed for Scala test provides. Same thing with, should be, or the various niceties that you get with Scala test or specs2. So another example might include, if any of you have worked with Scalatra or Spray for HTTP request routing, you would typically write your requests in a domain-specific language designed for that. Third example, building JSON HTs, right? So this is valid Scala code, but it doesn't really look like Scala, right? This arrow thing typically produces a tuple. It does not produce a JSON field. So there's a whole lot of, there's a whole mechanism under the hood that's designed to give you the illusion that you're writing in a domain-specific language, whereas in fact it's valid Scala code, it should be empty, and the collection is not empty. When evaluating that particular line of code, an exception gets thrown. So that is eagerly evaluated, right? The language that you use to describe the test gets evaluated on the fly. It does not, it produces effects, right? The result of a shallowly embedded DSL is an effect, which in the case of specs2 might be throwing an exception. If you use immutable spec, you would have to find some way to compose the results of these various assertions, and the result would not be an effect. It could be something else that we'll cover in a second. I prefer the term imperative DSLs, imperative because you give commands to your compiler, right? An expression in a shallowly embedded DSL is a command, whereas an expression in a deeply embedded DSL like SLIC, for instance, is something different that we'll need to define in a second. Examples of that might include AND tasks, right? Have any of you used AND in the past? Yeah, plenty of them, right? Because AND used to be the standard build tool for Java back in the day. So your AND XML gets read in by the AND runner, and little bits of it get executed on the fly. It doesn't read your whole description, try to figure out an execution plan. No, it just reads it line by line and executes it. A shell script might also be considered to be a shallowly embedded DSL if you implement it within a different language. Assertions, just assert, require, everything that you know from Scala, are also sort of a shallowly embedded DSL because things get evaluated as they happen, and exceptions get thrown as they happen. Conversely, deeply embedded DSLs are pure and lazy. These are languages that are designed not to produce effects, but to produce kind of execution plans that you later feed into some sort of execution engine. Right, so for SLIC, for instance, which I think might be one of the examples below, for SLIC, you would say something like, here is my users table, and I take users and map one of the fields out of it. Right, that does not actually do anything. It generates a description that you can later feed into SLIC for query evaluation, or for updates, or for whatever. But there is no effect to actually saying table.map_.field in SLIC. So the result is an execution plan that is a prescription. You prescribe a bit of behavior to subsequent logic, right? So the expressions themselves are pure and are lazily evaluated. And this is a very fundamental difference. Now, why would you choose one or the other? Well, obviously it depends on the context, but also there is a question of complexity. So deeply embedded DSLs are more powerful. You can do more things with them. If what you get is an execution plan and not an effect, you can take these plans, compose them together, do things like optimization, or for instance, with Java streams, Java 8 streams is one example of a deeply embedded DSL. Hypothetically, you could take all of the operations on a stream, everything that happens before your collect, right? Same thing with views in Scala, and you can fuse them to something that is more efficient. If you have a filter and a map, you could use flat map instead and do it in one step instead of two. Right? So there are various advantages to using a deeply embedded DSL, but they're more complex. Right? You need some sort of result model. If the result of an expression is an execution plan, you need some domain model, you need some classes to represent that execution plan. And then you need to write logic to actually execute that execution plan. Right? So it's a lot more complicated to set up. So it really depends on the level of complexity that you need and the complexity of your domain and what it is you're actually trying to achieve. For simplicity's sake, because we only have roughly 50 minutes, we're going to use an example that is shallowly embedded because it's just that much easier to showcase. So any questions so far before we actually dive into how to implement these in Scala? No? Okay. Are you worried? Bored? Oh, if you're not worried, you will be. If you're not bored, I'm sorry. Like I said, I'm sober. Okay, so when you're designing a domain-specific language, in Scala, really in any case, the first thing that you need to know is know your domain, right? You need to figure out what it is you're trying to achieve. And you know, the first thing you need to figure out is what are the various kind of actors at play, right? You're building a language, you're describing something. What are the things that are involved, right? What are the actors? What actions do they take, right? If you're writing a domain-specific language that queries a database, right? You're implementing SQL basically. Your actors might be, I as a user, I'm an actor. I'm trying to execute a statement. A table might be an actor. There are various moving pieces that you need to name, that you need to figure out what they are. So you have your actors, you have your actions, the things that the actors are trying to do. You have objects that the actions operate over, and you have some desirable consequences of that operation. So once again, for the SQL example, the consequence would be a query running on the database and data coming back, results that coming back to you, or it could be an update. Right, so it's very contextual. So let's use, we'll track this entire presentation, we'll track one example, which is data assertion or data validation. Very, very simple DSL for validating data objects. So in this example, you only really have one actor, and that is the user. Right? I'm a programmer, I'm writing my Scala code. I have, say, a case class or a bit of data that I want to validate. Right? So really there is only one actor and only one action. I'm the actor, and the action is validate this bit of data. And the objects that you have in place are, basically an assertion, right? If I'm trying to validate that a list is not empty, then the list is an object, and the assumption that the list is not empty is also an object. And the consequence that I want for this example is I want an assertion exception to be thrown if that assumption does not hold. So this is an actor, the color is an actor. Data and assumptions are objects, so we need to provide a language in which it's easy to define these assumptions. An assertion is the action that I'm trying to actually, act, right? The action that I'm trying to perform. And an exception may or may not get thrown. That is the consequence of this action. You also need to know your users, right? If you're building a domain-specific language, you're designing a language. People are going to want to use that language, hopefully. If you want people to use your language, you need to know who they are. You need to know what they're trying to achieve, right? So you have your users. Your user represents some actor in your domain-specific language. They have a desirable consequence, and what you're doing is you're designing a language that makes it easy for your users to express their desires, to express whatever it is they're trying to achieve in a way that is optimal for your domain. So for assertions, there's only one actor, there's only one consequence, right? I'm asserting that a piece of data matches the assumption that I have on its shape. The consequence is an exception that's thrown, so it's a very easy use case to showcase. But the real question is, if I'm providing an assertion API to my users, what is the best way for my users to express what it is that they want? Right? I have a list, I want to make sure that the list is not empty. What is the best syntax for my user to actually perform that, to actually express that in a language built on top of Scala? Well, the easiest way is to start with the user's perspective, right? I'm a programmer, I'm using this validation library. I have a piece of data. I want to make an assertion on the shape of the data. So really I need to provide two things. I need to provide a way for my user to define assumptions, right? I need to provide a language to say something like not empty, that is a language feature. And I need to have a very concise syntax for making assertions. So let's see what that, before we see what that might look like, there's also the question of vocabulary. Right? Every language is built of words or tokens. These words have semantics, have meanings. So we have our nouns that describe objects, we have adjectives that qualify objects, we have verbs and adverbs and all of that stuff, right? It's easy to think of a programming language and a domain-specific language as being something completely separate from English or Ukrainian or Russian or any really spoken language. But in effect, it deals with the same things. It deals with the transfer of information in a very precise and concise way. The idea is to express things as precisely as possible with as little information, as little words, as little letters as possible, while still making sense. So, for example, an assertion is a sentence. Right? I have this sentence, list should be empty. This is English, right? Ideally, I would want for my Scala code to look like, well, English or whatever language, right? But a spoken and well understood human language. That is the ideal. So we have this sentence, list should be empty. List is the object that I'm trying to assert on. That's a noun. Should be is the action, right? List should be something. That is the verb. And empty is the qualifier, the description of what it is I'm trying to achieve, and that is an adjective. So how do we start implementing this stuff in Scala? First, we need to figure out where the actor is. Because I've mentioned before, you need to identify your actors, and your actors perform actions. And there is no actor in the sentence, because the actor is implied, right? For this particular domain, data assertions, there really is only one actor, the programmer. So you don't really need that as part of your language. We might have a whole bunch of assumptions, right? This is the vocabulary for our data validation language. We have certain assumptions that we need to make, something like, emptiness for a collection or a list or a map. We have nullability, we have true, false for booleans, left, right for either's, defined, completed for futures, whatever. There is a whole stack of descriptive words that I can use that match the objects in my domain language. And also I might have parameterized assumptions. So if I want to say a string starts with another string, or ends with, or matches a regular expression, these are parameterized assumptions. So these are the words that make up my domain language. And once I've written all of this down, I have a good idea who my actors are, what actions they want, what consequences they want, a basic notion of what the sentence structure is for my language. I can start seriously thinking about how to implement it on top of a host language, and this is where we actually get to describe how these things work in Scala. So the second step is know your language. And by your language in this case, I mean know your host language. Know the features that the host language provides that allow you to actually implement DSLs. And Scala is quite unusual in that it's a statically typed language, but it's also very rich. It features, it has a lot of features that enable you to extend the syntax of the language with domain-specific considerations. So, tools of the trade, right? The toolbox that Scala gives you. It starts off with infix notation. Infix notation is also often called dot-free notation in Scala. And you've probably run into this, right? It's your ability to take this method call, this one parameter method call, what is called arity1. Any method call where you have an object, it has a method, and you invoke that method with a single parameter, you can in Scala write with no dots and no parentheses. Right? This is infix notation. These two sentences, if you will, in Scala are completely equivalent as far as the compiler is concerned. And this is the first step towards allowing natural syntax, natural DSLs. Because if you do not have this, your DSLs look kind of like fluent DSLs in Java. And fluent DSLs in Java don't really look like natural language, it just looks like a nice way of building stuff. Right? And we want an actual language in place. So this is the first thing that Scala gives us that really makes it possible to design DSLs. But, as with everything, there are caveats, right? It's not perfect. There are things you need to know about how this operates so that you don't paint yourself into a corner. Chaining, right? Infix notation is very confusing to Scala developers just starting their kind of foray into Scala, because list should be empty will not actually do what you think it does. You have your object, which is list. You have your method, which is should. And you would expect be empty to be the parameter. But in practice, Scala is very, very, very literal. So we expect be empty to be the parameter, but actually the compiler parses the code, and the parameter is in fact b. Right? It is very literal. It looks up the next token, and that is the parameter. It does not try to reason about, language constructions and whether or not this is a method call. No, it just takes the third token and treats it as the parameter. So you have to be a little bit careful. What is the type of b? I don't know. You probably didn't even define a type. B is probably a method in your DSL, right? It might have a function type, but whatever the type is, it is not what you meant, right? What you meant is for b empty to be the parameter, but Scala has, just goes on, says, okay, this is the token, right? And it treats b as your parameter. That is not what you intended. So you need to be a little bit careful. How do you, what can you do about it? How do you work around it? So the first thing you can do is you can contract it. If you've worked with, I think Scala Test actually has this for should be, one word, one method. This is a method name, right? And that is why. As simple as that. Should be just becomes the verb. That is one workaround that you can enact. A second workaround is to parenthesize. I think that is what Spec2 does. Different choices. Once you have this, b, because there's parentheses here, b is treated as a method call by the compiler, and then it takes the value of this method call and treats that as a parameter. So that is also a valid way to work around this issue. There is no right answer, right? A lot of times you might ask, which is better? There is no better. Right? The ideal solution would be to not have to worry about it and have the compiler figure out that, hey, it's English, you must have meant this to be a parameter. But it can't do that. Compilers are, they're not stupid, but they're very, very straightforward. Right? So it does not reason about your language. So really, pick one. There is no right answer. It's an aesthetic choice. It's a judgment call. Which one do you like better? Do you like parentheses? Do you like weird words that are actually two words in camel case? Pick one. Also, a second problem with infix notation, also around chaining. So you have the same sentence. List should be empty. You have your object, you have your method, and then you have your parameter, and then this gets evaluated into a result. Right? This is the resulting object from this infix notation method call. Now you have an object, and you have a verb, you have a method. Guess what you do not have? You do not have a parameter, right? So that is often surprising to people just coming into Scala for the first time, or they see something like, weird error messages that don't seem to have anything to do with what you actually intended. And that is why. Once again, it's a very, very literal-minded, very straightforward compilation process. The compiler does not know what you meant. It only knows what you wrote. So if you do not have a parameter, obviously you're going to get a compilation error. Right? So what this actually means in practice is for chaining to make sense, for infix notation and chaining to make sense, you need to have an odd number of parts to your sentence. You can have 3 words, you can have 5, 7, 11, however many, but it needs to be an odd number. You can't have an even number of parts unless you use something called postfix notation, which is deprecated from Scala to 10, I think, and you shouldn't. Right? It causes a whole bunch of ambiguities. There is a reason why the compiler will warn you unless you explicitly say that you want to use postfix operators. Just don't do that. Right? Use an odd number of words in a sentence. Any questions on this? No? Cool. Moving on. The next piece of the puzzle, the next feature that Scala gives you are implicit classes. So implicit classes really give you an entry point into your DSL. So in our example, we had, say for Spec2, we had string should not be empty. Should is not a member of string. You need to add it to string after the fact. That is an extension method in C#. In Scala, you do this through implicit classes. The extended type is domain specific. It depends on your language. So for data validation, because we want our language to be able to basically validate any data type, we would use a generic type, right? We don't know what it is we're extending. We want to add a should method to anything, right? To any object. So list should be empty. List is known ahead of time, right? This is the only thing really that we know ahead of time when our users are trying to validate data. Should be is the extension method. So we need to have a class that adds this. Also, one more use case for implicit classes, which we'll cover in a bit more detail later, is to lift values into the domain. Don't worry about it. I'm going to show that very, very explicitly in a few slides. Right? But really, your implicit class is your entry point because the only way to actually start a sentence in your domain-specific language is with a bit of data that is known that does not have this should be or should verb. So let's start putting it together. And this is where we actually start putting code on screen. I hope everything will make sense in a second. Right. We've established that an assertion is a sentence. In a sentence of the shape, some piece of data should be some predicate, right? A string should start with a sentence. A list should be empty. That is our sentence structure. So the first thing we need to do is we need to have some sort of definition of what a predicate is, right? We make it into a trait. I hope this is readable from the back. I'm sorry, this is I had hoped for a slightly more contrasty projection. So I'll just read it off for you. We have a trait called predicate. It has two methods. One method is called test, takes in a bit of data and returns a Boolean. Right? And it's generic in T in that a predicate can operate over some certain type T, and it can test that the prediction holds. Right? So if I say list is empty, T in this case would be a list of something. String, integers, etc., etc. And I have a failure message because, you know, the compiler can't guess what the predicate does. So the person implementing the predicate must provide a failure message. Next, we need an entry point into our DSL. So the only thing that we actually know ahead of time is the data. So we need to extend the type of that piece of data to actually support our DSL. We'll add an implicit class called validation context. It's generically T, operates over any arbitrary type T, and it adds this should be method that takes a predicate of T. And the implementation is not the point, right? The first thing we need to have is we actually need to have that entry point in our DSL. So we have our implicit class, and then because, as I said before, it's a lot simpler to implement shallowly embedded DSLs. What is the consequence of a failed data validation? For this example, an exception. Right? For simplicity's sake, let's just say that if any piece of data fails to validate, we throw an exception. It's like an assertion. Assertion failure has a consequence. That consequence is an exception being thrown. The implementation is actually pretty obvious, right? We have our implicit class, we have our should be method. We require, this is a Scala standard library. If you haven't run into this, I'm actually kind of surprised, but it's basically an assertion method that also exists at runtime, right? So it requires that the predicate can successfully test the data, and if not, then it just outputs a string, throws an exception with a string, value data is some sort of failure message derived from the predicate. So this is a brain-dead implementation that just throws an exception. So we can start implementing predicates, right? We have our extension method, we have this concept of the predicate, we can actually implement a predicate. So let's say our sentence, we want to implement an emptiness predicate for lists. Some list should be empty. Right? An implementation would be, fairly obvious, not entirely trivial, but fairly obvious. We have here an empty method that takes a type parameter T. T must be some iterable. It can be a sequence or a list or a map. It needs to be a collection, right? It needs to be iterable. And the predicate, the test is really simple. I take my piece of data that I know to be iterable, and I just ask, is it empty? And the message is not empty. So this is a very trivial implementation. So far, So far, it's pretty basic. So, are there any questions before we get to the nasty bits? Okay. Up until now, this is pretty trivial. If you've run into implicit classes, or you've implemented extension methods in C# or any other language that supports it, this is where, you know, given like half an hour, sorry about that, given half an hour of work, you would have arrived at this point, and everything would have been easy. This is where things get nasty, because Scala is not a trivial language, and there are all sorts of things that you need to take into consideration, and all sorts of corner cases that you need to handle in your DSL. This is why DSLs are actually not that easy to implement in any language in Scala. If you looked at the source code of Spex2 or ScalaTest or anything that provides a DSL, it gets kind of, you know, scary sometimes. So now things get hairy. Let's consider various corner cases that we might run into. Booleans. We want to have 3 times 4 is bigger than 10. That's a Boolean value. It should be true. The problem is that Booleans, the values for Booleans, true and false, are reserved keywords in Scala. Right? They're not values. They're actual keywords. You cannot provide a diff. Right? You cannot provide a method with the same name. You cannot provide an object with the same name. Really, you cannot define anything that has a name true or false in Scala, because you'll get a compiler warning. You can do that with backticks. Like you can wrap true in backticks, but then you would also have to use backticks whenever you actually use your DSL. So that is not really a solution. You know, rhetorical question: can we support the syntax? You know, despite the fact that these keywords are reserved, can we actually find a way to implement our DSL that will support this particular syntax? Obviously, the answer is yes. Otherwise, I wouldn't be wasting your time. One solution to that is to lift Boolean values to our domain model. What do I mean by that? We have our implicit class, Boolean predicate, that takes in a Boolean value and actually provides a predicate over that. Right? That is the way to go. Right? You have your should be method. In the signature, we're asking for a predicate, and what we're basically providing here is an implicit conversion from Boolean to a predicate of Boolean. Right? And the implementation is pretty simple. We have our test method, and it just checks that the value we got is equal to the value that is expected, and we have our failure message. That is an easy workaround, right? It's not trivial in that you need to think about it, and you need to be careful in your design to actually deal with these corner cases, but the solution is easy. So that is the first thing we need to do. Not a big deal. But then we have nulls, right? We have some string, and we want to say that some piece of data should be or should not be a null, right? The problem with null is that null is itself a reserved keyword and a value, so you also cannot use def and you cannot use object. More importantly, though, you would think that the solution of implicitly lifting null into our domain model would work, except not so much. And the reason is that this is the signature for should be that we started off with. Should be accepts predicate over some type T. Null in Scala is a bottom type. So any reference type, by definition, is a supertype of null. Right? So if you say should be null, null is actually a valid value for this predicate parameter. So there actually is not going to be an implicit search. An implicit search will not take place because, contrary to before, true and false are not of type predicate of T. So the compiler tries to find an implicit conversion to match that. But null is a predicate of T. It's a null predicate of T. So no implicit search will take place. So we need to, once again, find a horrible workaround to support that. Unfortunately, the only workaround that I'm aware of is providing an overload. Basically, you provide a second version of should be that deals specifically with nulls. And here there is a bit of a hitch. Right? Data validation can operate over anything. It can operate over integers, over lists, over domain objects. Null, by definition, only applies to reference types. So you want to, if someone says 5 should be null, you want to get a compiler error, because 5 by definition cannot be null. It's an integer, right? It's a value type. So what we do is a little bit of hackery. What we're saying is we have our should be overloaded that takes an n of type null. By the way, type null is not only bottom type, it only ever has one value, and that value is called null. Right? And we're asking the compiler to provide evidence to us that our type T is a subtype of any ref. Right? If you've never run into this pattern before, it might seem very, very confusing, but the way to read this is this method can only be called if the compiler can prove to this method that whatever type T is a reference type, because it is a subtype of any ref. Right? The syntax is a bit wonky, it can be explained, it's not that hard, but that is not the point. The point is you need to have this, otherwise your DSL is not sound. Right, and then we require the data is null, otherwise, because this should be null, and we provide the error message. Any questions on this? Yes?
Could we just provide, make should be except any, and all these our predicates like empty, like right, left, and everything, all they should extend the same trait for the predicate. And inside the should be message, we just do much, which checks for the type of the argument. And if it is a predicate, then we just do whatever we need to do with this predicate. And if it is not a predicate, if it is, for example, like this corner case like no, we do whatever we need to do with null.
Okay, so I'm just trying to understand. Are you asking, can we do the check at runtime, or can we provide some syntactic construct that resolves the different methods for these different use cases? Is it a predicate? Is it value, etc.?
Well, use much case structure.
Oh, so you use so you're asking about runtime dispatch. The question is, can we use pattern matching to deal with this? The answer is yes. But there are two problems with that. First, pattern matching happens at runtime, and we want to have as much compile time safety as possible. The whole idea in designing a domain-specific language is to add safety and sometimes performance, readability, various properties. Doing tests at runtime, first of all, is not a good solution because you don't get the compile time safety that you would with this weird solution. And second, it's a bit tricky to get right because, what if you forgot a case? You get a match error that is not sound, right? And also it does not perform as well because the resolution happens at runtime instead of compile time. So that, you could, but it's not an ideal solution. Any other questions so far? No. Okay, moving on. So this is a bit wonky, but it works. What about parameterized predicates, right? We have 3 times 4 should be equal to 12. Right, this is our sentence structure. This is what we ideally would like. Well, there's 2 problems here. First off, the equality predicate, just to set the stage, is pretty simple to implement, right? We have our equal to method, takes an attack parameter T, and the right-hand side, that's what RHS stands for, right-hand side of type T, and we just implement the predicate with a test method that tests for equality, generates the appropriate message. Easy enough. But we have an even number of parts in our sentence. Once again, we've broken the odd number of parts rule. Right, so what can we do about it? Oh, not much. The only solution that I'm aware of is to add parentheses. Right? 3 times 4 should be equal to 12. Now, there might be some other way to solve this, not one that I've run into. Every single library that ever gives you a DSL has this issue. In fact, I think ScalaTest has a specific section in its documentation titled, "What's up with all these parentheses?" This is what's up, right? There is no way around that. You just need to add parentheses, and if you don't like the way that it looks, well, that's too bad because you need to have it. There is one more consideration. We have just a bunch of examples here, right? ScalaUA should start with Scala. ScalaUA should end with UA. List 1 to 3 should contain 2. 5 should be greater than 2. There is a subtle difference between a few of these options. So, can you spot it? It's not really that tricky, right? Well, let me clue you in. We have here should and should be, right? And that is because we're trying to mimic English, and we're trying to have our sentences make sense. So actually, we have two predicate families, and I'm sorry for the technical language description. That's what Wikipedia says. We have simple modal form, so list 1 to 3 should contain 2. And then we have something called compound subjunctive form. I don't know what the hell that means, but that is what Wikipedia says is the right name for this type of verb, right? 3 times 4 should be equal to 12, right? So we have two families for predicates. We have predicates that require be and predicates that do not. So how do we deal with this? Well, it's simple enough. We add another verb. So we take our validation context class, we refactor the actual test and exception throwing to its own utility method that is private, and then we have two methods, should be and should, that both take a predicate, and we're good to go. Except this sucks. And the reason that this sucks is because it allows you to do things like list 1 to 3 should be contained 2, which is not English. Now, you have one of two choices. You can go the lazy route and say, well, if my user wants to write incorrect English, that's fine. Or you can go the anal retentive route, which is always the preferred route as far as I'm concerned, and find a way to deal with this. Find a way to disallow this type of sentence. Well, one way of doing this is, to find a way to differentiate between these two predicate families. So we take our base trait, predicate of T, and we extend it with modal predicate or compound predicate. And you'll notice we're not adding new features or anything. We're just classifying predicates into these two separate families. Next, we need to modify our verbs accordingly. So should takes in a modal predicate, should be takes in a compound predicate. Pretty simple. But we want to enforce the decision. We don't want anyone to be able to generate, just a predicate. We no longer have an action, a should or a should be, that deals with predicates. We just have those two types, modal or compound. So we make the predicate, the base trait sealed. We move it to a separate compilation unit. No one can extend it, and no one can actually use or instantiate a predicate of T. Nice on us. Finally, we need to go through all of our different predicates and classify them. Well, simple enough. Now we have a sensible sentence structure. Good on us. Lastly, we have negation, the not adverb, right, which so far I've ignored. But negating a predicate is not just about syntax. You expect to get a different message, right? If a list 1 to 3 should not contain 3, then you expect to get a different message from list 1 to 3 should contain 5, right? These are different error messages. So a predicate that the base trait, right, technically should support negation, and we need to extend it to provide us also a negative failure message. We need to extend the model, so the first thing, unfortunately, we need to do is decide what is the grammar, right? What is this going to look like from a user language perspective? We have two categories, and we have a number of options, right? We could go with the modal type of verbs. We can go with programmers should not start with Java. Or we could go with programmers should not wrapping start with Java, right? We have these two options we need to pick. For compound, we can have list 1 to 3 should not be empty, or list 1 to 3 should be not empty, list 1 to 3 should not be empty. All of these are valid options. There is no right choice, right? Some of them might look a little bit weirder, but it's an aesthetic choice. All these are reasonably valid sentences in kind of English, right? So you can use either one, and you need to pick. Once again, no right choice, it's an aesthetic preference. So for simplicity's sake, I went with programmers should not start with Java. So not is effectively a function that negates a predicate. Right? And we have should be not empty. Right? Might look a little bit weird, but it's a lot easier to implement, so that's what I'm going to showcase. Right? What do we need to do? We have our predicate T that we need to extend. Right? It's no longer just a test. It provides a failure, and it provides a negative failure message. Now, if you've tried working with variance annotations in Scala, this might look a little bit familiar. This is a kind of a hacky way, because what I need to do is for each, I want to be able to define a general negation method but the result of that negation would not be a predicate T, because we still have our two families. We have our compound predicates and our modal predicates, and we need to maintain that type information. Right? So we need to do a bit of type system hackery to figure out how to do that. So each type of predicate defines a self type that is a predicate of T, and a negate function that returns the self type. And this is just a type alias. It's ugly as sin, I know, and sometimes it's a little bit hard to understand, but fortunately you only have to do it once for the base predicate. So how would the implementation look like? You have your negative message, you have your generic negation function. Implementing it, just as an example for the modal predicate, would be, the self type is once again a modal predicate. If we're taking a modal predicate and we're negating it, we still expect to get back a modal predicate. And the negation is pretty easy. We just generate a new one. We invert the test, right? We're starting off with some predicate. We call it self. We run the test and we just Boolean negate the value of it. And then we switch the messages around. So the failure for the negative predicate is the negative message, whereas the negative message for the negated predicate becomes the original message. Right? We just invert it. And that way, we now have a generic thing that can basically negate any predicate that gives us a negative failure message. And once again, if you take a look at how Scala test or Specs2 deal with negation, this is exactly how it's done. Modulo implementation details. Finally, we need to add and this is my final slide, we need to add the not modifier, which is an adverb. So we have function not, operating over some type parameter T, takes in a predicate of T, returns, this is called dependent method types. You can actually do that in Scala if you haven't run into it. John Pretty, if he's around, might be jumping in his chair and enjoying now, because he really likes this feature. It returns the self type of the predicate. So if it's a modal, it returns a modal. If it's compound, it returns a compound. And it just calls negate. And this is part of our DSL now. And once we have those parts in place, voila. List 1 to 3 should be not empty. Programmers should not start with Java. All for the better. I was wondering if I should go with basic Ruby or Java, but I figured there might be Ruby programmers and basic is like easy to pick on, so Java. Right. So this works, and this is pretty much it. The next step in your DSL design is to sit back, have a cigar, drink some beer, and earn profit, which you're probably not going to because it's most likely an open source library and you're not getting paid for it, but never mind. Right, so this has been a lot of stuff. We unfortunately do not really, I think, have time for questions. Yeah, I need to stop in like a minute. If you have any questions, feel free to come after the talk and ask. There is a URL. I'm obviously gonna publish this slide deck on SlideShare. There are code examples that you can have a look that have all the things we discussed implemented, and it's on GitHub. If you have any questions, feel free to contact me. And that's all we have. Thank you very much.